What's the fundamental nature of reality? It's a massive question, right? But to even begin answering it, we need a map. Welcome to Cosmic Compass. Today, we're looking at the incredible tools we actually use to decode the cosmos. The story of how we understand our universe is absolutely packed with surprises, and we're going to dive right into it together.
We're funneling down through 5 quick steps today. We'll start with the bedrock of mathematics, move to the map of physics, cross the chasm of ignorance, catch some ripples in space-time, and finally develop a whole new sense.
Section 1. The bedrock of mathematics. This is where it all begins. Tracking this bedrock through time reveals a totally fascinating history. Because, math isn't just a modern invention, it literally originates in counting, going all the way back to prehistoric humans etching tally marks into bones. Then we see these huge leaps in antiquity, with Egyptian equations and ancient Greek geometry. Fast forward to the Middle Ages, and we get the concept of zero from India, negative numbers from China, and the very first books on algebra from the Islamic Golden Age. It's this incredible collective human effort that completely boomed into the modern age.
And this global effort created a really fascinating divide in modern numbers: pure versus applied math. So sometimes mathematicians just wander into the intellectual wilderness, playing with abstract concepts purely out of curiosity. That's pure math. But then an engineer or a physicist working on a cutting-edge real-world problem will suddenly realize that those exact pure equations, developed maybe 100 years ago, are the perfect tools to solve their current physics puzzle.
Just to keep us grounded in how beautifully weird pure math can actually get, think about topology. Topologically speaking, a coffee cup and a donut are the exact same thing. Topology looks at spaces where you can continuously deform shapes without tearing them. So, because they both have exactly one hole, a donut can mathematically be squished into the shape of a coffee mug. No way, right? But it's true, and these incredibly abstract rules form the true foundation of science.
Moving on to Section 2, the map of physics. Let's see how that mathematical bedrock actually builds the physical rules of our universe.
The crucial takeaway here is how physics basically branches into 3 main areas. You've got classical physics, dealing with the macroscopic world. Think thrown baseball, fluid dynamics, and good old Newtonian gravity. Then there's relativity, pioneered by Einstein, which deals with the extremely fast and the extremely huge, like the literal bending of space-time. And finally, quantum physics, zooming into the unimaginably small stuff, like atomic theory and the standard model of subatomic particles.
But as neat and tidy as that sounds, our maps are shockingly incomplete. We're missing massive pieces of the puzzle, which brings us to Section 3, the chasm of ignorance.
Here's the wild part. While we have quantum field theory, our best description of the universe completely fails to include gravity. They just don't mix mathematically at all. And if you look at the actual breakdown of our universe, a staggering 95% of it is made of completely unexplained dark energy and dark matter. Think about that. Everything we just talked about, Newton, Einstein, quantum mechanics, it all fits into that tiny 5% slice of known physics. The rest is a total mystery.
Section 4. Ripples in space-time. To peer into that terrifying 95% darkness, we have to look at relativity's wildest prediction.
Einstein predicted the existence of gravitational waves. We're talking about literal ripples stretching and squeezing the fabric of space-time itself, created when unbelievably massive objects accelerate. But for 100 years, they remained just a mathematical theory. We simply didn't know if we'd ever be able to build something sensitive enough to detect them in the real world.
Let's put the scale of what we finally found into perspective. Imagine the number 1.3 billion, because 1.3 billion light years away from Earth, 2 black holes, one 29 times the mass of our sun, and the other 36 times, were locked in a perilous death spiral, spinning at the frequency of a blender blade.
And then came the climax. In a mere fraction of a second, just 0.2 seconds, they collided at half the speed of light. When they merged, they formed a massive new black hole that rang like a bell. In that literal blink of an eye, they lost a mass equal to 3 entire suns. And thanks to Einstein's famous equation, equals mc squared, those 3 suns worth of mass were instantly converted into pure gravitational wave energy.
The sheer scale of this is almost impossible to grasp. That lightning-fast collision released 10 times more energy than the total output of every single star in the entire rest of the universe combined. It shot a colossal wake of gravitational waves outward in all directions at the exact speed of light.
Which leads us perfectly into Section 5, a whole new sense. Let's see how human ingenuity gave us a completely new way to actually catch these ripples.
You absolutely have to think about the timeline of this journey. While that wave silently raced toward us for 1.3 billion years, Earth went from a barren rock with microscopic sea creatures through the rise and fall of the dinosaurs, all the way to primates evolving into modern human civilization. And the most mind-blowing part? Humanity turned on its brand new wave detector on Saturday, November 12, 2015, just 2 days before the signal finally arrived. If we were just a weekend late, we would have missed it entirely.
Actually detecting this space-time ripple was an unbelievable feat of engineering. We literally had to build a machine sensitive enough to measure a distance 10,000 times smaller than a single proton. To put that into everyday terms, it's like trying to measure the distance from our sun to the nearest star to the exact accuracy of the width of a human hair. It's just wild.
So how does this technological marvel, known as a LIGO, actually work? Basically, an incredibly powerful laser is split into 2 separate beams. These beams then fly down 2 massive 4-kilometer-long vacuum tubes set in an L shape. They reflect off 40-kilogram pure silicon test masses, which are hung from the ceiling on a complex series of pendulums. And they do that specifically to insulate them from ground vibrations like passing trucks or even a scientist sneezing. Finally, the light journeys back, is collected, and recombined at the detector.
And here is where the absolute magic happens. Normally, if space-time is perfectly still, the 4-kilometer arms remain the exact same length. The lasers perfectly cancel each other out upon return, producing absolute zero signal. But when that ancient gravitational wave washed over Earth, it literally stretched and contracted the physical space of the building differently. The light traveled slightly different distances, arrived out of sync, stopped canceling out, and gave us our very first direct cosmic signal, which sounded like a tiny little boop.
For us, this is a total game changer. Until now, all our knowledge of the universe came from electromagnetic telescopes, looking at light, X-rays, and radio waves. But those telescopes are completely blind to these ripples. Gravitational wave astronomy proves without a doubt that black holes exist, proves these waves travel at the speed of light, and essentially gives humanity an entirely new sense. It's a brand new tool to start exploring that 95% of the dark universe we couldn't see before.
So I'll leave you with this provocative thought to ponder as we wrap up. If the foundational bedrock of math is just an abstract concept made up by human minds, why does it map the physical reality of our universe so flawlessly? And more excitingly, with our brand new cosmic sense turned on, what other invisible signals are out there in the dark, screaming toward us right now, just waiting to be discovered? Keep your curiosity ignited, and thanks for exploring this incredible universe with me.